So today I'm going to talk to you about exact change. And so in this lesson we're going to be computing the exact change in a function over a given time period by computing the area under the derivative curve of that function using geometry. So previously we had been using Riemann sums. This time we're going to be using geometry, and I think that's a blessing, right? Riemann sums were pretty difficult. So I'll give you a first example of a typical problem like this. And the example says, compute the exact change in the function with derivative f prime of x equals 1 plus x over 2 between x equals 1 and x equals 2. So one thing that's a little bit odd about this problem is I don't actually know what the function is. It doesn't tell me what the function f of x is. But that doesn't actually matter. All we want is the exact change relative to where it started. So it's enough just to know the derivative. So we're going to start by plotting the derivative. So the derivative is f prime of x equals 1 plus x over 2. And so the exact change in the function f of x, which has the derivative that we've graphed here on this chart, is going to be the area under the curve between those 2 points that we're interested in, x equals 1 and x equals 2. So these 2 points right here. So we're interested in just computing this area. So in this case, we can just use elementary geometry to do this for us. So I know that the height of this point here is 3 over 2. And I just got that by plugging in x equals 1 to my function here. So 1 plus 1 over 2 is 3 over 2, so that's why this thing is height 3 over 2. And I know that this height is 2, which tells me that this relative height here is 1/2. And so I've basically got two components to my area. I've got this triangle here, A1, and I've got this rectangle down here, A2. So the exact change is the total area A underneath this curve, and that total area is broken up into these two smaller areas, A1 and A2. And I can just use elementary geometry to figure out the size of A1 and A2. So I'll notice that the base of this rectangle has length 1. So that tells me that A1, which is the triangle on top, this thing has length 1 and height 1/2, and the area of a triangle is 1/2 base times height. So I got 1/2, 1/2, and 1. So the second term is A2, and that is the area of this rectangle down here. And this rectangle has height 3/2, and it has width 1. So the area of that rectangle is 3/2 times 1. So my total area is 1 over 4 times 1, so it's just 1 over 4, plus 3 over 2, which is 7 over 4. And that is my exact change. The exact change in my function between time t equals 1, or between time x equals 1 and x equals 2, is 7 over 4. All right, moving on. So the next thing that makes these problems kind of funny is that regions below the x-axis are treated as if they have negative area. So what do I mean by that? I'll give you an example. So the problem here says, find the total change in the function f of x equals x minus 1 over 4x squared on the interval from 0 to 3. So in this case, our interval is from 0 to 3, so here's 0, here's 3. So f prime of x is 1 minus 2x over 4, which is equal to 1 minus x over 2. So what does this derivative look like? We start at 1, and then we go down at a slope of 1/2, and then we eventually cross the x-axis, and we keep going. So where do we cross the x-axis? Well, it's when f prime equals 0. That's the same as saying that x is equal to 2. So this point here is x equals 2. So now we've got two areas. So the two areas are this positive area, which I've labeled A1 here, over to the left of 2. And then we've got this other area, which will be a negative area, to the right of 2. The exact change of this function is going to actually end up being A1 minus A2. So we're going to compute the areas of both of these triangles using just elementary geometry. And then to find the exact change of f over the whole interval, we take the area of the triangle that's above the axis, we count that one positively, and then we're going to add the area of the triangle that's below the x-axis. But because it's below the x-axis, we actually count it negatively, and that's why we get this minus sign here. The area of the first triangle is, well, it has height 1 and base length 2, so it's 1/2 times 2 times 1. So the area of the first triangle is 1. And the area of the second triangle is 1/2 times base times height, and the base of the second triangle is 1, and its height is 1/2. So 1 times 1/2. So that is going to be 1 over 4. And so our final answer is going to be the difference between those two areas, which is 1 minus 1 over 4, which is 3 over 4. So that is our exact change. Okay, finally, there's some other things that we can do using these techniques. For example, let's consider an object whose height at time t is given by some function at h of t. Now, again, the problem doesn't exactly tell us what h of t is. But it does tell us the derivative of h of t. It tells us that h prime of t is e to the minus t sine 2t. So suppose that we know that this is our derivative. The problem is asking us to find, at the time t equals pi seconds, is the object higher or lower than it was at the time t equals 0 seconds? So I'll start by drawing those two times on my axis. This y-axis is, of course, my t equals 0, and t equals pi is somewhere over here. So I want to plot this function. So when I've got a term like this out in front of a trig function, in this case I've got a trig function sine of 2t, the term out in front basically controls how tall the trig function is. In other words, it controls the amplitude. So in this case we've got a variable amplitude. So in that sort of situation, one thing you can do in order to plot the function, apart from just using a computer, which is also fine, but one thing you can do to plot the function is you can plot this variable amplitude function, which is called an envelope. And then within that envelope, your sine function or cosine function will basically behave as it normally does, but its amplitude is going to be changing, so it'll sort of bounce around within the envelope. I'll show you what I mean. E to the minus t looks like this. And if we reflect that over the x-axis, we get a counterpart to our envelope over here, so e to the minus t, and minus e to the minus t. And we do need that lower part of the envelope because trig functions also take negative values. And from there, sine of 2t basically looks like this, right? But instead of going up and down as it normally would with the same height, this time it's going to go up until it hits the envelope, and then kind of go down as it normally would, and then go down until it hits the envelope, and then go back up as it normally would. So if I draw that a little bit more accurately, our sine function basically looks like this. So I've got this a1 here, and then again I've got this other component down here. I'll call this a2. And because e to the minus t is decreasing, this area a2 is less than this other area a1. And from here we can just use our total change formula, which is we're going to add the areas above the x-axis and then subtract off the areas below the x-axis. The change in h of t is also known as delta h of t, or h of pi minus h of 0 is equal to a1 minus a2. And because from this graph, a1 is higher, it's a bigger hump than a2 is, this difference has to be positive. If you subtract a2 from a1, you have something left over because a2 is smaller. And therefore, in terms of our original problem, so this tells us that the change in h of t over the time interval in the problem is positive. So that means the object is higher. It's higher than where it started.